Today's topic is the volume of revolution about the x-axis and a solid that's formed. But we're going to start off with an idea of just looking at a cylinder. So someone just told me that they remembered that the volume of a cylinder is pi r squared times h. Now, if we think about why that formula is, or one of the ways that I remember that formula, is I think pi r squared is the area of a circle. And if we took one circle here on the bottom and colored it in, and then we took another circle and put over top of that, another circle over top of that, and kept adding these circles all the way up, we would get our volume. And sometimes I liken it to cutting pieces of paper and stacking them, because the paper, once it's all stacked, will be a volume that it covers a certain amount of space. But if we dissect it right down, we just have a bunch of circles that have been added up. How many circles are added up? Well, we multiply by the height to calculate how many circles we needed to add up. And this becomes the volume formula of a cylinder. Now we're going to take that idea of adding up circles, apply it to calculus, and apply it to integration. So integration, what it does is it finds an area under a curve. And if we broke it down, what it was a bunch of tiny little rectangles. And those tiny little rectangles that make them smaller and smaller and smaller basically come like thin, thin lines. So if I had one line here, and I could calculate that area, if I rotated that about the x-axis 360 degrees, can you see that that would make a circle? It would cut out a circle of that section. And if I cut out all different sizes of circles and stack them together, that would make the volume. In the same way that it made the volume in the cylinder. But now my circles are changing in size as I go. So this first shape, we have a big circle here, a little circle at the end, and different sizes of circles as we go along. The radius of these circles is like the area under the curve in a tiny, tiny little spot. If we took all of those radiuses and multiplied them by pi r squared, if we took pi r squared of all of those radiuses, we'd have all the circles put together, and that would make the volume. This is the idea for calculating the volume of a revolution. How do we find the area under the curve? That's the integral. What do we want to do with that area under the curve? We want to make a circle with it, which would be pi r squared. What's the radius? The radius is the function. So can you see that pi, this is my specific radius squared, comes up in this formula. And if we find the integral between two values a and b, it would break it down to get all of those circles, and all of those circles added up would end up making the volume. And this is going to be really cool because, okay, I'm going to get off topic. We're going to do some really cool stuff to start. We're going to start with our cylinder. We already knew the formula for it. If I have a line at y equals 2, and I take it from 1, 2, 3, 4, 1 to 5, and I take that line and I rotate it 360 degrees around the x-axis. Can you see that it would make, go down to here, and I rotate it. Can you see that it would make a cylinder? Okay. What do we know about this cylinder? It's on its side. We know that it has a radius of 2, right, if it was flipped up, and its height going from 1 to 5 would have a height of 4. We could use our volume of a cylinder formula, but what we want to see is, does the volume formula with integration work? Volume equals, bring the pi out in front, we're going from 1 to 5. What's our equation? Our equation was just 2. It's going to get squared because it's radius squared, dx, which would end up being pi from 1 to 5 of 4 dx. How do we integrate that? 4x from 1 to 5. Plug in 5 would be 20. Plug in 1 would be 4. According to this, it should be a volume of 16 pi. If we used our volume formula, we also get 16 pi, the same answer. Okay? Now, we had the formula already. We had the formula that volume was pi r squared times height for this equation, and that's how we could check. But let's say we wanted to make the formula. What do we put here instead of 2? Oh, here, I'll just draw a new page. I want to make a formula. So again, I'm going to rotate a line about the x-axis. But this time, I'm going to rotate the line y equals r. Some radius that I'm not telling you what it is, it's just r. Could be 2, could be 5, could be anything. And instead of going from 1 to 5, I'm going to start at 0 and go up to some height h. If I rotate this line, oh, this side should be dotted. Here we go. Perfect. And I draw this. Can you see that this is a cylinder with a radius r and a height h? Yes? And if I do the formula now, the formula says we need to go from 0 to h. My volume will be pi radius, because that's my function, squared. And so what will I get? I will get, this is radius squared x from 0 to h. Well, if I plug in h, I get r squared h. If I plug in 0, I minus 0. If I simplify this, I get the formula. So what I like about this is that it lets us create a formula. Maybe you forgot your volume. Well, okay. If you've forgotten your volume of a cylinder formula, most likely you'll forget how to do the volume of revolution formula. So I don't know if it would help you that way. But let's pick a formula that maybe you don't remember quite as well.
Area of trapezoid.
Well, we're doing volumes.
Volume of trapezoid.
Okay? Well, a trapezoid is two-dimensional. What happens if I draw this line? What shape is this? That's a cone. What are things that we use in our cone formula? We use the height and a radius of the outer circle. So now how do we take this and make a formula? If this is my radius and this is my height, this point right here, would you agree, is h comma r? What is the equation of this line? Y equals, okay, has a slope of r over h times x. Agreed? And so if I want to figure out what is the formula for the volume of a cone, and I'm going to use this idea that if I take a line and rotate it 360 degrees, I'm just adding up a bunch of smaller and smaller circles as I'm going along, and that's represented by the volume of revolution. I'm going from 0 up to h of, my function is r over hx squared dx. So I simplify this a little bit. R squared over h squared times x squared dx. And we can integrate. Remember, r and h are just numbers. The only thing we're integrating with to is respect to x. So now we would have r squared over h squared times x cubed over 3 from 0 to h. So beautiful. Plug in h, you'll get r squared times h cubed over h squared times 3 minus plug in 0. And when we simplify this, we get pi r squared, h squareds cancel out with an h left on top, divided by 3. Do you recognize that as your volume of a cone formula? And you see where the 1/3 comes in. Beautiful. Now, we showed this idea of adding up a bunch of circles could be used to find some formulas we already know. But now we can find all sorts of interesting volumes. Whatever shape is here, we can rotate it 360 degrees. We can square that function, and we can calculate its volume. And if you can calculate the volume of one shape, and you can calculate the volume of another shape underneath, can you see that if I wanted to calculate the volume of this bell, does that kind of look like a bell? You could have a function for the outside of the bell, figure out its volume of the whole thing, and then find a function for the inside of your bell and figure out its volume, and take the one volume and subtract the other volume, and you would get the volume. You could get a volume formula for a bell. That's cool. Okay, so let's look at a couple of questions. I won't get off topic yet. We'll do some regular questions first, then we'll talk about, if we have time, Gabriel's horn. Cool math problem. So we're going to start with find the volume of a solid that is generated under y equals x cubed from x equals 1 to 2 if it's rotated about the x-axis. Again, we need some skills in drawing, and we'll do some coloring skills just because it's fun. So, what does x cubed look like from x equals 1 to 2? It goes through 1, 1 and 2, 8. There is our function. And then if we're looking at it from 1 to 2, that's the part that we're going to rotate around the x-axis. So some help drawing these. I need to have, if this is my radius of 8, I need to make sure I put a dot equal distance below. Doesn't look too bad. And then to draw a circle in 3 dimensions ends up being an oval. So we have to sort of draw the best we can a circle there. And then we need to do the same thing here. Maybe there. And one of them, because the solid you wouldn't see the backside, draw it with a dotted line. Then copy the curve underneath. As far as really helping you see this, I find it's useful to bring crayons to class. Choose a color. I'll use red for the big circle, and then a different color and I think this helps you picture it more. Can you see the object now a little bit easier, that you've got the cross section red because it's bleeding because you just cut it? No, that's terrible. You've got the cross-section circle, and then the orange is the outside of the shape. So I sometimes find that by color coding things, or even if you have a pencil and you shade the one circle that's the cross-section, it helps you visualize the volume of the shape a little bit better. And so for an object that's rotated around the x-axis, we can find the volume by doing pi r squared, because that's your formula for a circle, and we have to add up all of those circles, so our integral will go, in this case, from 1 to 2. Our radius is the function x cubed. And our radius has to get squared, so our volume will be pi r squared. Then we need to simplify. This will become x to the 6 dx. And we do get an integral that we can do easily. Plug in 2. 2 to the 7, 128. Plug in 1. Ooh, 1 to the 7? No, too hard. I'll pull up my calculator. Okay. Minus 1 over 7, and subtract, we get 127 over 7 times pi, and that's the volume of that shape. That's amazing. So if we have the function, and that function is symmetrical all the way around, then you can find the volume of the shape. So now any vase that you find, if you can find a function that models the outside edge of that vase, you can figure out the volume of that shape. So I'd like you to try this one. You have to draw the picture and set up the volume of a revolution as best as you can. I'll put up the answer in a bit. First of all, the drawing of the picture. Did you get the square root moved 1 to the right? Correct. Then you can label those points. You have 1, 0 and 5, 2. So when you rotate it around, it makes a nice ham shape, maybe, if you were buying a big ham from the grocery store. And when you plug it into the formula, it's so nice because the square root and squares cancel each other out so nicely. And then we just have the integral from 1 to 5 of x minus 1. Which integrates quite easily. And if that shape was a ham, we now know that the volume of 1 ham is 8 pies. All right, let's do this one together, because now we're going to find a volume with a region in between two different functions. From 0 to pi over 4, and we're going to graph sine of x and cos of x. Now, for graphing sine of x, normally you would go all the way to 2 pi, divide things into 4 equal sections. I'm trying to spread this out. And goes up to 1, down to minus 1, and your sine graph goes from center line to your maximum, center line to your minimum. I'll draw my sine graph in blue. And it would keep going. And your cos graph, it starts at the maximum, center line, minimum, center line, maximum. How do I know they intersect at pi over 4? Well, maybe you think of your x, your x and y coordinates on your unit circle at pi over 4. They're both root 2 over 2. So it's a place where both the sine graph. And we want to find the volume of the solid that is generated when the region between y equals sine x and y equals cos x from 0 to pi over 4. So I'm going to shade that area in. Okay. We're going to go in crayon in orange. So this is the area between them. And we're going to imagine that area rotated around 360 degrees. So what we're going to do is to find that orange area. I'm going to use a lot of coloring here. Okay? We are going to rotate that red point, same distance down here. Draw a circle for that. Redraw our blue line underneath, which would be like that, and redraw our green line underneath, which would be like that. Everybody okay with that? Yes? I'm going to say that the volume of the green is the biggest one. If I was going to do that shape, I would have dark green here for this circle and a lighter green for the outside. Would you agree that that volume would be a solid shape of everything that we have? I'm not happy with my dark green. I need it darker. There, that's okay. Can you see the circle even darker here? And then what we need to do is find the volume of the blue. So the blue would be this part. Now, can you see if I had the green and I took away the blue, I would get let's see if this works. Okay. The green, take away the blue. Take away the green, take away the blue. That you would be left with just the orange. Can you imagine like a dog bowl, a water bowl for dogs turned on its side? Because you would have an outside shape, but a cone sort of, or a rounded part taken out of the middle. Now technically there would be a pin-size hole right at the bottom that was taken out. But maybe it's small enough that a water molecule couldn't get through, so you could still use this for a water bowl for a dog. And we want to find the volume of that water bowl because you have you love your pet very much, and so you're designing this fancy water bowl for your pet. You're going to make it, oh, it looks like gold. You're going to make it out of gold, and you want to use your skills in math to make a dog bowl that has both sine and cos represented in the bowl when it's made in the end. And it has to be made out of pure gold, so now you have to order gold on eBay to make it so you can melt it at home and make this. Because that's where you buy gold, right? You can buy just on eBay. Okay, good. So what do we need to do? We need to first find the green volume. Okay, I'll take out a green pen for that. My volume of the orange, volume equals in orange, is going to be the green volume, and the green volume was from 0 to pi over 4 of my green function was sine x dx. And then I'm going to need to subtract my blue volume, which also from 0 to pi over 4 is cos of x. So my volume is going to equal, for the green, pi, integral of sine, positive or negative cos? Integral of cos, positive sign, plug in pi over 4. What is cos of pi over 4? One over root 2 or negative root 2 over 2. Minus cos of 0. Cos of 0 is 1. Okay. Minus, in blue, sine of pi over 4. Root 2 over 2 minus sine of 0, 0. Okay, perfect. We found the mistake. Okay, right here, something felt bad because everything's negative there. And common sense says that you can't buy negative gold or the volume can't be negative. So we had to say, well, where did our mistake come from? And our mistake came from, in your notes, I apologize, but you're going to have to put an X through all of this nicely color-coded stuff. In my notes, I'm just going to nicely erase it. And we forgot to square, because it's pi r squared. Oh. And now we have a bigger dilemma. Can you integrate sine squared? You can't use substitution. If you tried to break it up with integration by parts, it might end with integration by parts. No, not well. Sorry. So instead, what we do is we use some of our properties for this one. Can you see that I could factor out a common factor of pi? That would leave me with my green integral from 0 to pi over 4 of sine squared dx minus my blue integral from 0 to pi over 4 of cos squared dx. And if I wanted to, I could just make this one integral from 0 to pi over 4 of the sine squared x minus the cos squared x. Any ideas here? That is an identity. That's why we have to have our identities memorized so that when they appear, we recognize them. Right? Just like your friends, you should memorize what they look like, so when you see them, you know what to call them. That is an identity. We can go volume equals pi 0 to pi over 4 sine squared minus cos squared is cos 2x. And that's an integral we can figure out. Plug in pi over 4, you'll get sine of pi over 2, which is 1 over 2, minus sine of 0, which is 0. And so our final volume is pi over 2. Whatever units you were using, you could go then and buy that amount of gold to build your fancy water bowl for your dog. Or your math teacher would also appreciate just gold in any form, whatever function you want. Wow, I just thought of a great hand-in assignment. Okay.